Hi folks, Kevin Carey from GE's Learning and Development Group. In this module, we're going to discuss the MDS iNET Series Transceiver, taking a high-level look at its key features and applications. We'll do a quick tour of the front panel interface and explain how cable connections are made to the unit. We'll also cover the steps in connecting a PC for radio configuration and introduce you to the built-in configuration tool. Please remember that this learning module is simply a starting point. There are additional tools available to you online, including other videos, electronic manuals, and firmware downloads for the product. We'll cover how to access these near the end of this module. Let's begin. The MDS iNET is a license-free, long-range wireless solution for use in industrial monitoring and control. It is frequently used in utility applications such as water, gas, electric, or oil facilities, or in other industrial processes and monitoring applications. Collectively, these applications are referred to as SCADA, an acronym for Supervisory Control and Data Acquisition. To be clear, the radio does not perform the actual monitoring or control. That's the job of a connected RTU or similar device and its associated sensors. The role of the radio is to convey this data reliably across a wireless network, connecting sites together without the need for hardwired cabling. The iNET supports both IP Ethernet and serial connectivity. When the iNET radio was first introduced in the early 2000s, it represented a new era for GE MDS. Previously, the focus of most radios for SCADA applications was on serial-based connectivity. Leading an emerging trend in the market, the iNET provided the ability for IP Ethernet connectivity and serial connections right at its front panel. This allowed immediate use with devices employing newer Ethernet-based technology and also provided serial to Ethernet bridging capability, an important factor for mixed systems or for those on a migration path to Ethernet. A higher speed iNET-II was later introduced, more on this shortly, and either model can be configured by the user as an access point or a remote. Both iNET models have stood the test of time, providing a balance between data throughput and wireless transmission range. So let's review just what the iNET series offers. It provides a secure, industrial-hardened solution for wireless connectivity over long-range signal paths, and it does so under unlicensed spectrum rules available in the US, Canada, and many other countries. The primary band of operation is the 902 to 928 MHz spectrum. Special frequency bands such as 300 MHz, used principally in China, also exist, but the focus of this module is on 900 MHz, and this is denoted by the model number of MDS iNET-900. The primary functions of the radio are similar regardless of the frequency of operation. The iNET carries both serial and Ethernet data over the air, achieving Ethernet speeds into the megabit class. When we speak of transmission range, we need to make a distinction between the common Wi-Fi solutions that are so prevalent today and the iNET radio. Where Wi-Fi is intended to provide coverage in the vicinity of a given location or a campus, the iNET is capable of ranges easily exceeding tens of kilometers under favorable conditions. Paths of 32 kilometers are known to exist. This class of range is achieved through high receiver sensitivity, transmitter power output up to 1 watt, the permitted maximum, and the use of an external high-performance antenna at radio sites. The iNET series uses frequency dispersion techniques known as frequency hopping spread spectrum, FHSS for the iNET, and digital transmission system, DTS, for the iNET-II model. With these techniques, the transmitted signal is rapidly switched over a wide swath of operating frequencies within the operating band. This is a key to license-free operation, and it minimizes the effects of possible interference to and from the radio. It also serves to enhance the security of transmitted data. The radios in a given network follow the frequency changes in the same pattern as the transmitting station, so that reliable communications is maintained. Any missed data due to channel interference, for example, can be retransmitted until the complete packet gets through with an acknowledgement. Also, a limited number of channels or zones may be eliminated from the operating patterns to deal with frequencies having constant interference. As with our other self-contained transceiver products, the iNET is housed in a rugged die-cast aluminum enclosure, providing physical protection as well as RF shielding. The radio is designed for use in harsh environments and demanding industrial applications. It operates in the temperature range of -30 to +60 degrees Celsius and need only be protected from direct exposure to the weather. Special enclosures are available to house the radio for outdoor installations or for redundant configurations with a backup radio. MDS iNET transceivers meet some of the most demanding product specifications in the industry. The product is approved for use in CSA Class 1 Division II environments, has IEEE 1613 approval for use in electrical substations, and it supports industry standard signaling protocols including Modbus TCP, DF1, and IEC 61850. The iNET is designed to be as plug-and-play as possible, requiring a minimum of setup for initial operation. The transceiver comes in two primary models, access point and remote. Every iNET system must have at least one access point or AP radio. A unit can be configured by the user to operate as an access point or remote with some restrictions as described in the manual. Additionally, three types of remote gateways are available: the Ethernet bridge, the serial gateway, and the dual gateway, supporting both IP Ethernet and serial services. Security is an important consideration with any industrial wireless solution. The MDS iNET series leads the field in this area with built-in AES 128-bit encryption for the iNET-II and RC4 128 for the iNET, dynamic key rotation, virtual LAN segregation, and password-protected login access. These measures, in addition to its frequency-agile transmission, make the iNET series an extremely secure choice for wireless signaling and control. Now, let's talk a bit about the two different models of iNET radios, the basic iNET and the iNET-II. Although the iNET and iNET-II have the same outward appearance, there are important differences, and these submodels are not over-the-air compatible. A given network must contain radios that are all of the same type. A label on the bottom of the radio indicates the type that you have. An iNET radio can operate at a data rate of 256 or 512 kbps at a channel size of 316.5 kHz. By contrast, the iNET-II is an enhanced model offering higher throughput speeds of 512 kbps or 1 megabit per second, but at a correspondingly wider channel size of 600 kHz. Increasing data throughput always requires more channel bandwidth, and this is a function of physics. Higher data speeds also require stronger received signal strengths as compared with slower speeds. We'll talk more later about optimizing signal strength through proper system design. As compared to regular frequency hopping techniques, the iNET-II uses DTS, or Digital Transmission System. DTS comes under different certification rules and employs specific channels, not zones, for transmission. Frequency hopping is not required under DTS, but the iNET-II does employ hopping to achieve the same benefits that are realized with the iNET transceiver. DTS rules limit RF output power to a maximum of 8 dBm per 3 kHz. Thus, the iNET-II's power output comes factory set to plus 29 dBm. That covers some of the high-level features and benefits of the iNET platform. Next, we'll talk about how it can be used in the field and how a number of iNETs can be used in a network arrangement. We'll focus on the most common point-to-multipoint applications, but the iNET can be used in point-to-point networks, in backhaul service for other radio systems, and even for mobile operation. As mentioned earlier, the iNET is commonly used in SCADA applications by utilities and other distributed operations. Shown here is a common arrangement where utility data is being linked from field sites, such as that shown at location 1, to an access point pictured at site 2. In turn, the access point communicates with a data control center at site 3, where the data is processed and where outgoing commands originate. In some cases, the access point would be located directly at the data control center, provided the terrain and elevation would allow for adequate coverage to outlying sites. iNET signals travel primarily by line of sight. A mobile installation is also shown in this example. This might be used by personnel who visit remote sites and enter status or log in transactional data. Mobile range is typically reduced because antenna heights are lower, non-directional antennas are used, which means lower gain, and there are signal fluctuations of a moving vehicle. Still, through proper design, a mobile range of about 4 kilometers can be achieved over favorable terrain. The system pictured could have a large number of remote sites, although just one is shown here for clarity. Long-range wireless connectivity reduces the need for drive time of personnel, allows immediate action on changing conditions, and provides a constant view of network activity. Operating parameters of the radio can also be monitored and controlled remotely. This includes reprogramming, signal quality checks, firmware downloads, and so on. In summary, the wireless system takes the place of a traditional Ethernet or other wired network, and it does so over a wide geographic area. Let's take a look at a typical radio site, in this case a remote one. There are 3 basic requirements for proper installation: a stable DC power source, an effective antenna system, and the proper connection between the data equipment and the radio. The effectiveness of the antenna system cannot be overemphasized. Antennas must be designed for the frequency band of operation and should be mounted in the clear, above and away from any obstructions that might limit or block signals to and from associated sites. The coaxial feed line must be of a low loss type and should be kept as short as possible. This is generally true of all cabling on site, but is especially important for the coax if maximum signal levels are to be achieved. The power supply must be capable of delivering 10 to 30 volts of well-filtered DC, negative ground, at a current level sufficient for the radio. Power requirements are marked at the radio's power connector. A current capability of 2 amperes is sufficient for most installations. Data connections will be to the radio's LAN port, serial port, or both, depending on the arrangement of the system. The PC shown here is typically used for configuration at the time of setup or for maintenance activities and does not need to be connected full-time. An access point would be similar, but would typically use an omnidirectional antenna to provide equal coverage to all remote sites. We'll cover making cable connections to the radio shortly. We've talked in general terms about the iNET and how it is used in the field. Now let's take a close-up look at the chassis itself and explore the connectors and indicators provided on the front panel. The MDS iNET is housed in a compact aluminum enclosure, providing physical protection as well as RF shielding for the circuit board inside. The unit contains all circuitry needed for operation and requires only the attachment of proper interface cabling to the front panel connections. LED indicators on the top panel show key status of the radio, and we'll cover these in more detail soon. The enclosure measures 11.2 centimeters deep and 17.2 centimeters wide. As seen in the second image below, the height of the unit is 3.5 centimeters. Here is a bottom view of the radio with the standard flat mounting brackets attached. Only the provided screws should be used for attaching the brackets. 2 mounting positions are available to provide for mounting flexibility. The position shown is the most common arrangement, where the center-to-center distance between bracket holes is 18.4 centimeters. The spacing between holes on each bracket is 7 centimeters. Let's take a close-up look at the LED indicator panel. From left to right, we have the LAN indicator, which lights to show that a locally connected area network has been found. It blinks to show data activity being transmitted and received on the network. In some cases, the LED may glow dimly to indicate heavy network traffic. The COM1 or console LED blinks to show transmit-receive data activity on the radio's COM1 connector. This port is used for attaching a configuration PC to manage the radio. The data or COM2 LED blinks to show activity on the radio's COM2 port. This port is used to connect serial equipment to the radio, such as a remote terminal unit, RTU, or other data equipment at the installation site. Next, we have the power indicator, which lights to show that DC power has been applied. There is no on-off switch on the radio, so this LED lights whenever power is present. It does have one other purpose, however. A rapid flash of the LED indicates an alarm condition, which can be further investigated using the management PC. Finally, the link LED, when lit, shows that an over-the-air RF link has been established with another station. It blinks to show RF activity. It's good to become familiar with all of these indicators, as they provide a quick way of determining the radio's basic status and are a valuable aid when checking for network difficulties. We'll talk more about front panel connections shortly, but first let's identify what connections are available. All connection points are located on the edge of the radio, as shown here. You'll notice that each connector is positioned beneath the LED indicator that pertains to it, as just described. Starting from the left, we have the LAN Ethernet port, which is the common type you're probably familiar with on PCs and routers. Next, we have the COM1 and COM2 serial ports, respectively, and these are of the DB9 type, used for connecting a PC and other serial data equipment. Next to that is the radio's power connector, a 2-pin locking type, used to attach DC power to the radio. Always check the label above this connector to determine the proper input for your particular unit. Finally, we have the RF antenna connection for the radio. This is a coaxial type TNC connector commonly used in such applications. It connects the coaxial cable that leads to an outdoor antenna. In some cases, such as a short-range link, a flexible antenna might be directly attached to this port. Next, we'll cover making actual cable connections to the radio. This is intended to be an overview, so you should always consult the documentation sent with your radio for complete details. Seen here are the items typically supplied with an iNET radio. Besides the radio itself, there is a quick start guide, a small card telling you how to download the full technical manual, mounting brackets, in this case already attached to the radio, and a DC power connector. With the radio ready to install, we'll now run through making cable connections to the front panel. First, we'll make the LAN Ethernet connection. This accepts an RJ45 modular plug commonly used in data networks today. It simply pushes in until it clicks, locking it in place. Next, we'll make the COM1 connection, which is often used for serial-based management of the radio. COM2 is next, which is also a serial port and used for connection to data equipment at the radio site, such as an RTU or PLC, programmable logic controller. The antenna port accepts a type TNC coax connector. This is typically going to connect to the station antenna. In some cases, a small flexible antenna may be directly connected here, as described earlier. With our cable connections made, it's time to connect the DC power to the radio. We save this for last because it's advisable to not have the radio transmitting without a proper antenna or RF load attached. Our power plug here has already been wired with the correct polarity and is ready for insertion. Always check the label above the radio's power socket for proper voltage and polarity. We'll go ahead and plug it in. will secure the two binding screws. This prevents accidental disconnect of the cable. And this completes attachment of all interface cables to the front panel. There are no manual controls or adjustments on the radio, and all configuration is done via a connected PC. Next, we'll cover how to launch a management session and prepare the radio for configuration. There are several ways to connect to the radio, including serially through the COM1 port using a console session, through the LAN port using a web browser, or through the LAN port using the Telnet application. You'll need to use the COM1 method, serial, if the unit's IP address is unknown. The default address on units shipped from the factory is 192.168.1.1. In the example here, we'll be using Telnet, as it provides a nearly identical experience to serial, yet provides the flexibility of connecting through the LAN Ethernet port. The IP address is known in this case, so it is a straightforward option. Note that we've gone into the Properties menu of Telnet and changed the screen background to white and the text to black for improved visibility. Normally in Telnet, the background is black with white text. There are a number of appearance options you can set in the Properties tab for Telnet. So, to launch a Telnet session with the radio, we're going to simply type the radio's IP address at the Telnet prompt as follows. We're going to start with the word Telnet, all lowercase, a space, and then the IP address, in this case 192.168.1.2. We press enter, and we see the default name for the unit, which is iNET. We are also prompted for the password below this. The default password on a new unit is admin. Ordinarily, you'll want to change this as soon as possible for security, but we'll use this default for the example. We'll enter this now, ADMIN. You note that it does not show on the screen for further security. We press the enter key, and it connects us to the radio, opening the starting information screen. Now this is the beginning point for all operations. From here, we can view the device mode, where we see that this unit is operating as an access point. We can also see the device name, network name, IP address, overall status, the running time, and version information for both hardware and firmware. We can also view the unit's serial number. Once we're ready to go to the main menu, we press G, and you'll see this shown at the bottom of the screen. Okay, so I've pressed G on the keyboard, brings us to the main menu. This allows us to access all configurable items for the radio, each within a submenu represented by a letter. You see numerous selections here. Let's look at item C, the radio configuration menu. I type C on the keyboard. Here we see several parameters that can be viewed or adjusted. For example, the RF power is currently set to 20 dBm or 100 milliwatts. So let's turn it up to the maximum allowable of 30 dBm, which is equivalent to 1 watt. We press the letter A, corresponding to the RF output power selection. This places us into the edit mode. We type the new power level, 30 dBm, press enter, and the new power is displayed. Now let's step back to the main menu by pressing the escape key as shown at the bottom of the screen. And let's select item E, the security configuration submenu. Here we can go into further submenus that control the device, wireless, and radius security properties. Radius is a robust security scheme that uses a shared secret phrase required to gain access to the network. Let's step back again to the main menu by pressing the escape key. Now let's enter the performance information menu screen. Letter G. And the performance information screen is going to provide us information on RSSI, which means Received Signal Strength Indication, allows us to look at logs and statistics, and even view information for associated remote radios. We'll jump back to the main menu once again. As you can see, there are many items that can be accessed using this configuration tool. Unlike earlier products that had some manual controls and adjustments, all management of the iNET radio is done through software. This is just a brief tour of the menu in keeping with this overview module. However, the product manual and other online resources will give you complete information for using the menu system. We've completed our overview of the iNET itself, but there are many online resources that can help you get the most from your product. We'll cover these next, along with how to use the online store for ordering the product and related accessories. As mentioned earlier, the full technical manual for the radio is accessible online for download. This is done for two reasons. First, it ensures you always receive the latest available copy. And second, it provides you with a searchable electronic version that can be accessed anywhere you have an internet connection. The manual can be printed, stored on other media, or sent to others as necessary. We'll run through a quick example of how to access the manual here. First, we bring up the GE MDS website, which can be found by entering gemds.com in your browser. We'll use the product lookup tool on this page to locate the iNET product. Now this is arranged alphabetically, so under the first tab, A through I, we find the iNET at the bottom of this list. Click on that. Under the Resources tab, you see several selections here. We're going to click on Manuals. Now this shows all available publications for the iNET product line. For the full technical manual, we are going to want the 05-2806 AL1 manual located here. We'll click on that. It gives us the option to open or save the manual. Now we're going to click Open for a quick view in our case. Manual downloads. It's going to take a little bit of time at 5.6 megabytes depending on your internet speed. And here you see the manual open. Widen the screen a little bit, center this. Now you can use the online table of contents to jump to various sections in the manual, or you can scroll manually, just as with any PDF document. Okay, with the manual closed, we're back at the original listings page, and you can see there are many other publications available for the product, including the startup guide, versions for earlier runs of firmware, and other bulletins pertaining to the iNET. We're going to jump back one page where we began, and you see the online version of the brochure, but you can also download a printable copy of the brochure here at the bottom left. You can also download software and firmware for both the basic iNET and the iNET-II. Let's move on to the online store. We access that by clicking the title for it at the upper left side of the page. Here, we'll want to hover over the Industrial Communication tab, and then go down to Wireless LAN Extension. Move over to the right and we see iNET listed here. We'll click on iNET-II for our example. This is the order page for the product. You'll see not only the radio itself, but also common accessories listed below. You simply select the items you need, add them to your cart, and then click the Login button to complete your order. If you don't have login credentials, that's no problem. You'll have the opportunity to register at this time. That completes our basic tour of the online store. This completes our overview module for the MDS iNET Series Transceiver. We invite you to stay in touch with GE's Learning and Development Group for more training opportunities. The address shown at the left side of the screen will provide you access to many more videos for GE MDS products. Thanks for watching, and we'll see you again soon.